Hello everyone! Today we'll talk about the problem reveal cards in increasing order. Here we're given a list of unique integers representing cards in a deck, and the following procedure is performed on the deck for as long as it's not empty. We take the first card of the deck and remove it. We take the first card of the deck, move it to the back. Take the first card of the new deck, remove it, the first card move to the back, and so on until we remove all the cards. And we're interested in the order of the removal. Specifically, in this problem, we want to rearrange the deck in such a way that the order of removal is exactly the sorted order of those cards. Let's first make sure that we understand the procedure. So, in this case, we start with a deck 1, 2, 3. We take the 1, this is the first number we remove. Then we have to move the 2 to the back. Then we select the next number. And then the final number is a 2. If we move it to the back, nothing changes. So this is the last number. The order is 1, 3, 2. The first easy thing to notice when thinking about this problem is that we don't actually have to think about moving numbers to the end of the queue. Instead, we can just imagine that we're going to skip all the numbers that were already taken. So here we have a longer array, and we take a 2, skip a 1. Take a 3, skip an 8. Take a 9, skip a 4. Take a 5, skip a 1. Take an 8, skip a 4, take a 1, and finally we're left with a 4. And this is the order that this procedure would work on a longer array. Okay, so now we know how this procedure works, but that's not the problem that we're being asked to solve. We're being asked to find an order of the deck, an initial order, such that after this procedure, this output is sorted. There are many ways to approach this problem. I recommend that you think about some of them. By the way, there's also something that's called Josephus problem. You might want to look it up on the internet, because it's a very similar idea, and in this case, since we always skip just one card, so we move one card to the back of the deck, then many solutions will be possible here, but if this number was greater, then it might be much more difficult to solve this problem quickly. And then some of the theory about the Josephus problem might come in handy, but we don't need it here. Now, while the problem is not about simulating this process, that simulation will be an important part of any solution, so let's talk about how we can do it. One easy way, which you might want to implement yourself, is to just do essentially what I did before. So you go through the array as many times as you need to, you jump over all the removed elements, you skip every second element, and you take every second element. And if your first intuition is that this will be O of n squared, then, well, first of all, actually in this problem, the bounds are lenient enough to accept that, but it isn't O of n squared, because you're going to be going over the array many times. But how many times? Well, first, you're going to remove half of all the elements, right? Then half of all the remaining elements. Then half of that half, and so on. How many times you have to add those removals until you remove all n elements? Well, that's exactly how many times you have to halve n, right? Divide n by 2 until you run out of elements. So that's exactly the logarithm of n. So this is going to be actually n log n, only log n iterations over the array. Another way to simulate it, which is actually in linear time, because we only skip one card every step, is just to use a simple data structure, a simple queue, and simulate this process as it's given. So the remaining part is to actually solve the problem, in the sense that we want to somehow get to an ordering of our original cards that will give us the sorted order at the end. But to do so, we only need to actually take, let's say, all the numbers from 0 to n minus 1, and so on, see what the result is after we pass them through our procedure, and then we know at what position the appropriate card in the deck has to fall, so that it will go to the answer at the right step, right? So for instance, here 0 is first, 2 is second, and so on. So this position 0 has to be the smallest element, position 2 has to be the second smallest, and so on. Let's see the details in code. We're going to be simulating the process on numbers from 0 to n minus 1. And remembering the order they appear at output, after the whole simulation. And the simulation is very simple. we remove the left element, and then we add the next left element to the end. We do that for as long as there are any elements. And that is the output at which those indices will be in the answer. And now we only have to sort the deck, because we have to make sure that the final order is sorted, so we have to know that final order. And now we know that for every position in the output order, the correspondingly ith smallest, right, for the ith position in output order, the ith smallest element of the deck has to be on that position initially. So we just assign it, and that is exactly the ordering that will be sorted after this procedure.